Afternoon. It's a great pleasure to be here with old friends like Ashok and also young friends, which I cultivate now. And I thought when I came for the PhD vibe of Stanley, I should give a talk, not directly on my research. COVID is not hovering around, and he's sitting there. Okay, so I thought it is better to give you a flavor of one of my pet topics, cyclic voltammetry. Of course, I do also research a little bit using various electrochemical tools. The reason why I choose this topic are multifold. First reason, a lot of people use voltammetry, especially cyclic voltammetry. So that is why I have shown a picture, cycle connected with a voltmeter. Just show that is a wrong perception. Nothing to do with the cycle. Cycle, of course, you can say starting point and come back. And voltmeter, many proposals and papers write cyclic voltmeter, which is totally wrong. Okay, cyclic voltammetry is the technique. Cyclic voltammogram is the result which you look at it. So a lot of misconceptions in cyclic voltammetry. There is an astounding variety of people who use cyclic voltammetry for preliminary information. Astounding variety because battery engineers use it, biochemists use it for developing biosensors, semiconductor physicists use it, polymer coating, barrier layer properties. So lot of people use, variety of people use it. And why is it? Because without knowing the details, this gives you some diagnostic criteria. Anybody can look at a voltammogram and say reversible, irreversible, or quasi-reversible, something in between based on rate constant. And then people can also say whether redox active, redox inactive. That is why, without knowing anything about electrochemistry, if you look at voltammogram, you can understand, you can explain. That is one reason. Interpretation is very easy. If you want to go do quantitative analysis, you need to learn electrochemistry. You have to need, at least you need to learn Baden-Faulkner. Some chapters you have to read, diffusion equations you need to understand. So whether you want very qualitative discussion or semi-quantitative or really rigorous, all these are possible. That is why this technique is very popular. There is one more reason. The other reason is, if you look at the excitement and the promise of developments happened during last 20, 30 years in this area. For example, there are eye-opening developments. Microelectrodes, 1 micron, less than 1 micron, implanted on brain, monitor the neurotransmitters such as dopamine in hippocampus or amygdala. So highly localized monitoring of neurotransmitters is possible by using this technique. So neurosurgeons use cyclic voltammetry to find out how much dopamine is there in a small zone. Similarly, you will see other people. I told you about semiconductor physicists, silicon, passivation. So this is the reason why voltammetry is extensively used. Organic chemists use it to understand the mechanism. A radical cation or radical anion is formed. And then what happened to the fate of it? How much, whether disproportionation or solvent, with it reacts with the solvent. So the lifetime also can be monitored. Carbene generation, electrochemically carbocation generation. So organic chemists use it for understanding their mechanism. This is the reason why the technique become extremely popular. Apparently, whenever you have popularity, misuse is more. Okay, anything very highly popular, people will tend to misuse it. That's the reason why I thought I should talk to you on voltammetry uses and misuses or abuses. So I already talked to you about it. This is a typical voltammogram. You will see something going up one direction and something coming down in other direction, current enhancement. From a physical chemistry perspective, this simple diagram can give you a lot of information, wealth of information, kinetics and thermodynamics. Simple kinetics because you record this, remember you are applying a very small signal and you traverse from one region to other region and come back. Now, thermodynamically, you will be able to look at what is this potential, something called half wave potential. Half wave means you have a full wave at the peak, but half of that is very important. So if you know these potentials, you will be able to get free energy value. That is why the thermodynamics is important. And if you know potential and free energy, suppose you do this at 2-3 temperatures, then you have got dou G by dou Tp, which is entropy. So equilibrium constant, entropy, then free energy, changes with respect to solvent, with respect to some additives you add. This is the thermodynamic information you get. Nothing happens, you will get an equilibrium constant value. How the equilibrium constant changes with respect to additives. So one side you get thermodynamic information. Now you come to kinetics. We are talking about reversibility, irreversibility, quasi-reversibility, depends on the rate constant. So rate constant can be quantitatively measured by using this technique. Again, if you understand the theoretical formalism, so much information you can get it. Sometimes you get a pre-wave, sometimes a post-wave. So all these are important because certain phenomena, adsorbed molecule and freely diffusing molecule, the reactivity is different. You have an electrode-electrolyte interface. Interface means there is strong electric field. I have a species here, ferrocene, imagine, acetonitrile and ferrocene. Ferrocene will slowly come closer to the surface, undergoes an electron transfer, ferrocenium cation is forming, and it normally goes out. Once it is the cation is forming, it will migrate to the other side. Now, sometimes the ferrocene in solution and ferrocene adsorbed on the surface, reactivity can be different. Slight change in free energy. All that can be studied rigorously by using voltammetry. So as I mentioned, does it move? Yeah. So as I mentioned, I will not be able to tell you all that, but I can give you a flavor, a snapshot of voltammetry, cyclic voltammetry, focusing more on the misuse or confusion side. I would be talking about what is voltammetry, the basic principle. Little bit of quantitative aspects will be touched here and there, but that is not essential for you to understand. So if there are difficulties with respect to rate expressions or some few mathematical expressions, don't worry, you can skip that and still you will be able to understand that. Advantages and limitations is what I'm going to focus more. Common mistakes in representation as well as extracting parameters from voltammetry. If you have a voltammogram with you at very low scan rate, high scan rate, doesn't matter. Because when you change the scan rate, you are also changing the rate at which the system you are being probing. That's why the time scale can be varied. So one of the beautiful thing about voltammetry is with your fingers, you can vary the rates of where the electric field is applied. Very slow, very high. How slow it could be? Microvolt per second. How high it should be? 5,000, 50,000 volt per second. It doesn't damage your system because you are doing it fast, That is why certain proteins, electron transfer, you want to investigate, you have to go to 50,000 volt per second. Otherwise, you will never be able to capture the rate process happening for this cytochrome. Many examples are there. So the beauty of this technique is time scale is for you to decide very slow or very fast. Now, whenever we talk about the time scale, we have multiple processes happening on the electrode-electrolyte interface. Charge transfer, the rate processes, and diffusion. Mostly the competition is between these two, diffusion and electron transfer. So kinetics depends on whether diffusion is slow or electron transfer is slow. Both this can be investigated by changing the scan rate. When you have such a voltammogram, apparently I told you we have to do some corrections. Need for corrections I will explain, and few applications I would illustrate. But again, I will not go to the details. If any of you want to know more on that, I am available. We can have a discussion. The last topic I would like to talk to you also is something I mentioned to you, very small electrodes which can be implanted. They could be carbon fibers of even sometimes single wall carbon nanotube. 1 nanometer, 2 nanometer is also possible. Just implant on a part of a biological species or living creature and you can record. Very well-known experiment was done in 20 years back. A rat is moving. While the rat is moving, an ultra-microelectrode is implanted in his brain and you record voltammogram. You also show some food to the rat. That will move closer to the, why food? Because you will have some obsession with some special food and certain parts in the brain. In neurologists use action potential, but voltammograms will give you discernible differences in dopamine. Dopamine is the one which is responsible for obsession, addiction, such things. Its concentration can be monitored by using voltammetry. So that is why one of those images I showed you where microelectrode implanted in brain and you record that. So in electrochemistry, we have various tools. We classify all the electrochemical techniques into 2 or 3 types. First, we call it as equilibrium technique. Equilibrium technique is where you use only Nernst equation. You don't pass any current, but it can give you again information. Mostly you get thermodynamic information. For example, just a simple open circuit measurement, potentiometry we call. So the parameters which we vary for understanding equilibrium processes are apparently concentration, because Nernst equation means you need to change concentration. Some cases you measure capacitance, potential variation with the temperature. That means you create an electrochemical cell. You have a working electrode where you are interested in processes happening there, either oxidation or reduction. And you keep on varying concentrations. Some cases you keep on varying the counter ions, ions which are not directly involved in the reaction, but they influence these processes, mass transfer processes close to the electrode and in the electrochemical cell. That's why all these parameters are important. Sometimes surface tension, sometimes capacitance, and variation of temperature. But all these are done without passing current. And you have a great advantage because since you are not passing current, you can look at equilibrium phenomena. Sometimes for supercapacitors, absorption, how much capacitance is changed, potential dependence of capacitance, all that can be studied by surface tension. For example, from surface tension, you can get some of these parameters. This is all equilibrium information, thermodynamic information, but never miss it because this is a prerequisite. Any electrochemical measurement you want to do, first you must understand the equilibrium phenomena. Open circuit potential measurement is the key. Then only you should pass current. So second type, we call it as transient techniques. Transient means you are looking at variation with respect to time. So current time transients, call it as chronoamperometry. Potential time transients, chronopotentiometry. And charge time measurement, chronocoulometry. All three are complementary techniques. Yeah, you can get information about kinetics. Sometimes relaxation layer can be obtained, and all this could also be interpreted by using equivalent circuits. Normally, people use equivalent circuit only for impedance. No, but equivalent circuit is the same thing. Capacitance, resistance, etc. can be used to understand also chronoamperometry and chronopotentiometry and chronocoulometry. The other technique is steady state technique, which is extremely important because reliable information. Tafel studies, many of you must be doing Tafel mechanisms. You have a current versus low current versus potential measurement or potential measurement. They are more reliable. Then lastly, we classify AC and DC methods. AC means impedance technique. And I will not go to details. So in all these measurements, our objective is to understand rate processes. So in electrochemistry, you always express rate in terms of current, I by NFA. I by NF, F is Faraday, N is the number of electrons involved, and current always expressed in current density. Even if you don't know the actual area, you find out some apparent area. If you know the surface roughness by techniques such as atomic scanning tunneling microscopy or atomic force microscopy, you can get an accurate value. But in any case, we use relative area. And the parameters are current, potential, charge with the time versus, this is what happens. And our potential is very important because once you understand equilibrium phenomena, you apply external electric field. Low field or high field. Sometimes you apply very low field so that potential shift is linear. It is easy for us to understand because we are in the linear domain. So that tools we use are shown, 2-terminal and 3-terminal. 3-terminal is much more reliable because you will be able to change the potential on the working electrode very accurately. So these are preliminary aspects of electrochemistry. With respect to this, we can look at cyclic voltammetry. What do we do in cyclic voltammetry? We have an electrode. It is in equilibrium with an electrolyte. There are species moving around. There are counter ions, solvents, supporting electrolyte. They are just, passively watching what is happening at the interface. So interface means there is a very high electric field. Although you may measure 0.3 volt or 0.2 volt, please understand that this voltage is localized in few Armstrong, 5 Armstrong, 10 Armstrong. So the field gradient is very high, 10 power 3 to 10 power 4 volt per centimeter. So such a high field is responsible for you to do certain reactions at 800 degrees in a furnace, similar to that in electrode-electrolyte interface. So number one is that is the reason why many processes normally which you can do at very high temperature can be done at room temperature by using an electrode-electrolyte interface. The high field is responsible. So what we have is you have a potentiostat which will give you a small, what you call linearly varying potential. You can control that. We have a function generator coupled with a potentiostat and you do the measurement. I've also shown a cell there. Maybe, inorganic chemists use a cell with either a nitrogen or an argon environment so that the complexes are stabilized. And then you use working electrode of various nature. Sometimes platinum, sometimes glassy carbon. And the reference electrode is very important. Reference electrode, normally people use 3 types of reference electrode. Actual reference electrode means you should be able to measure the potential very accurately. That means a metal, equilibrium with a metal salt with a high solubility product, and then there should be a common ion. So in alkaline medium, you should use mercurous oxide. In chloride media, you can use silver chloride or probably calomel, but you can't use calomel for any medium, especially non-aqueous. So acetonitrile, dichloromethane, at such cases, we use a non-aqueous Ag plus reference electrode. If these reference electrodes are not available, then people use a platinum wire or a silver wire, and you can calibrate separately. These are called quasi-reference electrodes. So quasi-reference electrodes are not as correct as original reference electrode. Quasi-reference electrodes give you 50 to maybe even 60, 70 millivolt difference. So you should keep it in mind that suppose you want to investigate a carbene, you may not be able to get a correct reference electrode. You can even use a platinum wire and then do platinum wire as a quasi-reference electrode. Sometimes you can use an internal reference electrode. That means you use platinum, you don't know, but the system is acetonitrile or dichloromethane. After doing all the experiments, you put some ferrocene and measure, express your potential by using ferrocene, FC plus as an internal reference electrode. So keep in mind all these are important because when you look at the accuracy of these measurements, they all affect your measurement. So cyclic voltammetry and linear sweep voltammetry, the phenomena is one and same. Linear sweep means you have an equilibrium value, no Faraday reaction can happen. From there, you slowly vary the potential, go to your final value. This is what is called linear sweep. Now, linear sweep voltammetry or cyclic voltammetry itself, accurately, it is called double step chronoamperometry. Double step because one step and then you come down. So the actual term is quite complicated. We all call it as cyclic voltammetry. The phenomena we look at is similar to initially a potential where no Faraday reaction happens. That means system is truly equilibrium, but no reaction happens. You know the potential. Now I slowly change the potential. Some point a reaction happens. There the redox Faraday current starts going. The onset of that point is very important. And then you go there further, reactivity increases. The species which is formed as a result of the Faraday reaction get consumed faster and faster, and you get a surface concentration of 0 of the species. It is so high. This is what you get as a peak in voltammetry. This is called diffusion limited current. In polarography and all that, same concept only here. Cyclic voltammetry was invented by actually a person using polarograph, Randles and Sevick. Both of them were using mercury drop electrode. That is why the origin. Anyway, that is not important. So initially one potential to another potential. That means we are applying a potential. You can apply a potential step and look at the current variation. But instead of step, we are giving a slowly increasing or decreasing ramp. Ramp rate, scan rate is important. When you apply potential step, what do you do? Initial potential, no reaction happens. Final potential, in between reaction happens. Then look at the current flow. So in cyclic voltammetry, to understand voltammetry, first we must know current time variationship. That is why chronoamperometry is the basis of all these voltammetric measurements. In chronoamperometry, what you do? Initially, there is a potential. No reaction happens. You apply a potential, in between reaction starts and look at the current variation with respect to time. So this expression is very well known called Kotel equation. So to understand voltammetry, first point is Kotel equation. Current, Faraday current is initially 0 at some value, initial value. Then I change the potential in another potential value where current start flowing, and the current variation with the time. It's purely diffusion control. So current I depends on N is number of electrons, Faraday, area, concentration. D is the diffusion coefficient. Pi power half, T power half. This is the expression. So current is varying with respect to T power minus half. This expression is called Kotel equation. Kotel equation is obtained assuming linear diffusion. Linear means if this is my electrode, species is moving, diffusing closely to the electrode surface. I'm forgetting about convection, forgetting about migration, also forgetting about other modes of diffusion. No linear. That means dC by dx only I consider. dC by dy is 0, dC by dz is 0. Linear diffusion. Now, you can see what happens. E1 is the initial value, E2 is the final value. So I am applying a step from E1 to E2. What happens? The concentration of initial CO star is the surface concentration. As a result of the reaction, slowly the buildup of the layer happens, diffusion layer. That is the time is very important. How thick the diffusion layer can form, we can calculate. This is called Nernst diffusion layer thickness. If I know the diffusion coefficient, I should be able to calculate how much time it takes. So you can see now current variation. So we are looking at concentration is varying with respect to time. Since concentration is varying, time and current and concentration, there is a dependence. And as a result of that, current variation with the time is what I monitor. So this is all very well understood using conventional diffusion theories. We call it as chronoamperometry. You can see now current, I mentioned you now. Interestingly, instead of current, if I monitor the charge, that means quantity of current flowing. Instead of I measure integral of I into T, total charge. If I monitor the charge with respect to time, I have a lot of advantages here. Quarterly equation tells you current variation with respect to time. I is proportional to T power minus half. If I plot Q is the charge versus time. Very interesting plot. There is a plot called Anson plot. Simple quarterly plot is current versus time, but Anson plot is quantity of current versus time. You can see below the expression. The images are more or less similar. Only difference is that instead of current, I am plotting charge. What is interesting is Q, total Q, I can get Q diffusion. Only the diffusion part I can separate. Q absorption part I can separate, and Q double layer. So all these three can be quantitatively separated if I plot charge versus time. Again, I'm only showing a snippet of this. I will not go to the details. So we have looked at an equilibrium value. No reaction happens. One potential step, and current versus time by quarterly equation. Same thing I can do little more rigorously by plotting charge versus time. So in voltammetry, I will use two. One, E1 is the initial value. I go to E2, another value where E1 to E2 reaction happened. E2 to E1 I am coming back. During that, the reverse process also happened. So the basis of cyclic voltammetry is a double potential step. Except that instead of potential step, I am applying a ramp. To understand that, you can see this scheme. E1 is the initial value. E2 is the final potential. I go from E1 to E2 in a scan. I go in a ramp manner, linear sweep. Similarly, I come back to E2. So this is why voltammetry is sometimes called double step chronoamperometry. Linear sweep voltammetry's correct term is double step chronoamperometry. Imagine anthracene in deoxygenated DMF. Deoxygenate because we want to remove all oxygen. We don't want oxygen reduction. So anthracene is put, and let us say I am going to anthracene can become anthracene radical cation, and when I reverse it, radical cation can get consumed. So please look at the second plot. Current as per quarterly equation, a decay, and then all of a sudden I am changing the potential to the final value. I'll see a reverse decay. So this shows a typical reversible pattern of a double potential step. Last one is quantity of current versus time, chronocoulometry. So both this, the difference is that Q versus T enables you to calculate some more detailed aspects of mechanism. Sometimes adsorption aspects, sometimes double layer changes with respect to counter ions, all that can be studied. So remember, chronocoulometry and double potential step chronometry, they are all cousins of cyclic voltammetry. So in cyclic voltammetry, what we do is, or linear sweep voltammetry up to that, we are actually looking at current, time, and potential variation simultaneously. Although in the voltammogram, you plot current and potential. Potential is linearly varying with respect to time. So it's a composite parameter because E is equal to E0 plus or minus nu into T. Nu is the scan rate. So linearly increasing or linearly decreasing potential is Y. That is why actually by doing voltammetry, you are getting a cross section of this particular three-dimensional diagram. You have current, time, and potential. So voltammetry is very popular because you can sweep across this. All the three variables simultaneously you can change and find out what is happening in your system. Example, start with initial, E initial, starting point. This is important that E initial should be always open circuit potential, because open circuit potential, you understand, open circuit potential is steady state. It doesn't change with respect to time. It doesn't change with respect to, maybe slight changes will be with respect to temperature. So it is good to also equilibrate at least few hours, make sure the potential is steady state. If potential is varying, then you need to understand why it is varying. Some film is forming on the surface, some composition is happening. That is why initial value must be open circuit potential. From there, you apply linear scan, go to a value. That value is called switching potential. So what is shown here is anthracene or naphthalene or any aromatic hydrocarbon you take, you will see when you go, you reduce them, you will be able to see a radical anion just formed, and then that decomposes. So the last plot I have shown is the concentration profile of the reactant as well as product. Please remember that the surface becomes zero concentration. That is where the peak comes. So any voltammetric peak means you are getting a diffusion limited value. The surface concentration of whatever, let's say O. O is the species. O diffuses, come to the electrode surface, undergoes reaction. O takes up an electron forming R. This O initial concentration is CO. CO is the concentration of O you added. CO naught or CO star is the concentration on the electrode surface. So CO minus CO naught is the concentration gradient divided by the distance. That is exactly what is important in voltammetry. So what is plotted in the last one is reactant and product as a function of time. This is where the diffusion layer is forming. This is all the more important because when we see ultra-microelectrodes, very small electrodes, diffusion layer thickness should be smaller than the electrode dimension. So what is a small electrode, ultra-microelectrode? An electrode whose dimension is much, much smaller than the diffusion layer thickness. That is very critical. Now, in cyclic voltammetry, initial value, go to E lambda. E lambda is the switching potential. And then come back, maybe to your original value, E initial, but it's not mandatory. You can go to any other value also to see the fate of what has happened. So potential profile is shown in first one. Switching time, you can see lambda, E lambda is the switching potential. Current, you can see how the current varies. Current, all of a sudden it increases. That arrow is shown in a region where corresponding to E0 prime, formal potential, E half. That is where the onset of the reaction happens. By the time you go to the tip, already the surface concentration is 0. So A plus E giving a radical anion, anthracene, naphthalene, that is the value. P corresponds to surface concentration of this as 0. And then there is a decrease. That decrease is quaternion. That means exactly as predicted by Quaternion equation. That means T power minus half dependence you will get. That is why in cyclic voltammetry, the waves are not well defined. The diminution part, you can actually plot it with the T power minus half and do calculation. Extrapolation can be done. Simulation of voltammogram, people use this. So I have just shown you a reversible picture there, resulting voltammogram. So what first we show is potential sweep and the resultant current flow. Potential sweep can be done very slow or very high. This is for us to decide. I will not go to the quantitative details, but when I say I am giving a potential sweep, what I do is E of T, EI initial value, plus or minus nu into T. Nu is called scan rate. Scan rate is an important parameter. So now for reversible, irreversible, quasi-reversible systems, quasi-reversible means the rate constant some number is fixed. Both positive, both forward and backward will contribute. Such cases the treatment varies. Reversible system, starting point is Nernst equation. I'm sure all of you know Nernst equation, but we write Nernst equation slightly different way and write the concentration of O and R. Please remember CO and CR are surface concentrations. 0 indicates on the electrode surface and both are varying with respect to time. That is why CO and CR are function of distance, function of time. To understand accurately, we write CO 0T and CR 0T. That means concentration of O and concentration of R at the surface for a given time. And that is given by only Nernst equation. Nernst equation E is equal to E naught into CO by CR. E is equal to E naught plus or minus RT by N of CO by CR. So CO by CR we are writing as E power. Only thing is the potential now, it is not just one potential. Initial potential minus the time dependent, standard dependent potential variation and the formal potential. And now this could be solved. I will not go to the details. You can numerically solve it. Finally, you will see current as a function of some parameter where T is very important and sigma is also very important. With respect to all this, if you plot, you will get an voltammogram. So theoretically, it is possible for you to get an voltammogram if you put all these numbers. That is why these days, cyclic voltammetry, whenever you study, you use a commercial instrument, they will give you a software to simulate the voltammogram. Sometimes even freewares are available for you. If you put the values of diffusion coefficient, concentration, all that, you will be able to get voltammogram. Remember, this is helpful for you to quantitatively calculate parameters. For example, if you get a voltammogram like this, of course, forget about this axis. This axis is called current function with a lot of diffusion coefficient, many other parameters come into picture. But remember that when we get voltammogram, theoretically it is possible to get this voltammogram, and you can classify this voltammogram into reversible, irreversible, quasi-reversible based on rate constant. Rate constant actually is not only rate constant coupled with the scan rate. Rate constant also depends on how slow or fast you are scanning the potential. That's why the last three, reversible, Nernstian, parameter, artificial parameter called lambda is given. Lambda is nothing but lambda consists of rate constant and scan rate. If you assume scan rate is 100 millivolt per second, that means square root of scan rate is 10. You will get rate constant 0.32, maybe some 10 or 50 centimeter per second. So any process such as ferrocene oxide, ferrocene ferrocenium, or potassium ferricyanide ferrocenide, or ruthenium hexamino, all these cases are reversible because rate constant is much larger than 0.3. 0.3, 10, 100, they are all centimeter per second, they are all reversible. The other extreme side is totally irreversible. You can see lambda less than 10 power minus 2, 1 plus alpha. Alpha is called transfer coefficient. Don't worry about all that. Look at only the rate constant. 10 power minus 5. Nu power half means 100 millivolt per second, you can put it as 10. So anywhere the rate constant is lower than 10 power minus 4 is irreversible. In between 10 power minus 4 centimeter per second to maybe 1 centimeter per second is considered quasi-reversible. So this is an arbitrary classification. This is valid only for a macro electrode. When you use very small electrodes, this will change. But understand that even if you don't understand all this, look at voltammograms. You will have a forward, you will have a backward, and you can calculate the full width at half maximum, FWHM. It will give you some number. For example, peak current. Peak current for a reversible system is proportional to nu power half. So peak current as a function of square root of scan rate you plot, you will get a straight line. And if you know the diffusion coefficient, you can calculate N. If you know N, you can calculate diffusion coefficient. That is why this is very important. For people who use biosensors, their interest is only CO star. That is why glucose oxidation, you do various, and you can make a calibration plot. One of the important advantages of this quantitative analysis, measure the full width at half maximum. What is called peak potential, then you have EP half. That difference is well defined. For a reversible system, you get 56.5 by N. If N is 1, you will be able to calculate. So the number of electrons involved can be calculated from this. Look at this base, what is called the down. There is something called baseline. Baseline means without adding the reactant, like no ferrocene or no potassium ferricyanide. You have only the solvent, supporting electrolyte, and record the voltammogram. So you can also do a baseline correction and then calculate. So typically we calculate all these parameters: EPA, anodic peak; EPC, cathodic peak; E half, E0. All these are important to help you to understand voltammograms. I will not go to the details. Diagnostic tests are there to decide whether it is reversible, irreversible, quasi-reversible. Reversibility can be proved by using any of these parameters. Delta EP, that means difference between the cathodic peak and anodic peak, should be 59 by N millivolt for a reversible system. 59, yeah, I'm sure you know RT by NF when N is equal to 1. EP minus EP half, again 59. Ratio of the cathodic to anodic currents, IPC by IPA. IPA is anodic, IPC is cathodic, is unity. IP is proportional to nu power half. EP is independent of scan rate. So if it is a reversible system, you can record so many times voltammograms at various scan rates. You can see that peak potential will be independent of scan rate. And at potentials beyond peak, you will see a quartile type of dependence. Anyway, you can see now in the same diagram, as you decrease the rate constant, how the voltammogram changes. Peak potential becomes more and more difficult, more and more accessible, more and more energy is needed to be spent to have the reaction. That is why the peak is shifting. At the same time, you will see the width also is going to be larger and larger. That means as the rate constant comes down, you will see the width again increases. Now, what we saw here are diagnostic criteria for reversible. You go to irreversible, you will get similar parameters. No reverse peak, highly irreversible system. In quasi-reversible, you will see both. IPC proportionate nu power half again. EPC shifts 30 by alpha C into N alpha. What happened alpha C? Alpha is called cathodic transfer coefficient. N alpha, number of electrons. But problem now is, if you have got more than one step, what is the rate determining step? The rate determining step, how much is N? That is why N alpha means corresponding to the rate determining step. Again, you have similar criteria. I will not go to details. Reversible, irreversible, and quasi-reversible. Quasi-reversible also you can see EPC shifts negatively with increasing nu. Now, let us see some examples. We have looked at the theoretically what is reversible, irreversible, and quasi-reversible. You can see now one extreme case, highly irreversible system. You will see plots are very broad. You have only something very difficult for you to even delineate what is the peak potential. Look at the initial value. Initial value is important. Here, for example, hydroxyferrocene, reduced and oxidized. This is such a fast reaction that you can apply. You can get parameters such as E half can be obtained. Equilibrium constant can be calculated from this. And if you do at various temperatures, you can also calculate thermodynamic parameters such as entropy of the system. Only difference is, please remember, there is E naught prime. E naught prime is called formal potential. We don't know the activity. So we may not use the accurate value of activity. What you measure, is okay. Anyway, I'm almost, another 15 minutes. It is there. It is moving. Yeah. Yes. Look at this. Oxidant to reductant. We don't know the activity. So we use E naught prime is the formal potential. Whatever concentration you know, you use it. Activity coefficients are not easily available. That is why in this case, you can calculate the parameters. You go to kinetics, you will see now, vary with the scan rate. Please remember that the peak potential is independent of scan rate. You go from 50 millivolt per second to 500 millivolt per second, peak potential is same. Shows typical reversibility. Now, scan rate, current, peak current versus square root of scan rate, it should pass through origin. That shows that you have got essentially a reversible system with, you can calculate from this a diffusion coefficient. What is shown here is a simulated with these numbers, area 0.1 centimeter square, rate constant 1 centimeter per second. That means a really reversible system and E naught value. You can apply Randall-Sevick equation. You can calculate. Randall-Sevick equation tells you IP proportional to these parameters. Now, what is interesting here is Randall-Sevick equation, you have to understand that we are talking here, both oxidant and reductant are soluble. When you apply without discriminate, without understanding to a supercapacitor or a battery because something is already on the electrode surface. So there will be always differences. Ideally, Randall-Sevick equation is where both oxidized and reduced forms are soluble. That solubility is very important. So if a product is forming on the electrode, the concentration variation happens and deviation happens. How do you know deviations? First thing is that it will not pass through origin. Origin, peak current versus square root of scan rate passing through origin is an important test that you will see. Most of these cases that will fail because you may not have a freely diffusing redox system. Typical example. This is again from our own studies. We have been preparing very small gold particles, 2 nanometer, 3 nanometer. They are protected by a monolayer. They are stabilized by monolayers such as octane thiol, sometimes oleamine. These monolayers, the gold particles are 3 nanometer, 4 nanometer. Based on the size, they can freely diffuse in the electrolyte to the electrode surface. And one of the remarkable properties of these small gold nanoparticles is they are multi-valent. They can become 1 plus, 2 plus, 3 plus, 4 plus. This is really a size-dependent phenomenon. The moment you cross 6, 7 nanometer, this disappears. This is called multi-valent redox behavior. And the person who investigated this mostly is Royce W. Murray, chemically modified electrodes. He died last week, North Carolina University. Last 30 years, outstanding work in surface modification, electrochemistry. Just 1 week back, he passed away. Okay, Royce W. Murray, a chief editor of analytical chemistry for, I don't know, last 20, 30 years. So Royce W. Murray investigated so much of small gold nanoparticles. Now, we have been working on graphene quantum dots and gold quantum dots. Both of them show these multi-valent redox phenomena. Why is it interesting? Because look at the voltammograms. Cyclic voltammograms, when you record, you may see it's a noise. You can see now, where I'm talking only this curve, okay? This curve. So you see small wavy things. But when you take a derivative, you will see that, there are a lot of peaks. So this is to show that you may miss such information. So this is where the power of voltammetry is shown abundantly. You have a cyclic voltammogram, many times you throw it as some noise coming from somewhere, but you take a derivative, you will see that beautiful redox phenomena are unraveled here. And this will be as a function of scan rate. And I mentioned you quantity of charge, how much is absorbed, etc., can be obtained from this one. Now, we have done an independent technique. Independent technique is called differential pulse voltammetry, another technique where you apply small pulse. Differential pulse voltammetry will give you compared to cyclic voltammetry, differential pulse voltammetry is 1,000 times more accurate. Very small concentration can be detected. So that differential pulse voltammetry also confirmed that gold small particles give you multi-valent redox properties. Now, this is gold as well as graphene quantum dot. So what is interesting here is 2.2 nanometer, 3 nanometer, 2.8, etc. gives you more or less similar such redox peaks. And you look at this E versus Z. Z is the charge number. The diffusion coefficient of these particles can be obtained by using cyclic voltammetry. Again, I will not go to details. When such a phenomena happens, adsorption also can be understood much more thoroughly by using voltammetry. We use an approach called a Laveron approach. Laveron has done a lot of work on adsorption systems. With a function of scan rate, you plot voltammograms, plot peak potential versus scan rate, and you will get a logarithmic expression. Again, I will not go to details. I only want to tell you that whenever adsorption is rate determining, Laveron approach enables you to calculate the rate constant of adsorption. For example, here 2.2 second inverse. So all these are possible by using cyclic voltammetry, provided we understand it quantitatively. If you don't understand quantitatively, you can also do a lot of work, electrocatalysis. Look at this cyclic voltammogram. This is what is called, you see the peaks. Butterfly pattern in cyclic voltammetry. Why is it butterfly pattern? Look at the potential. This is sulfuric acid only. This is a cyclic voltammogram of platinum, polycrystalline platinum in sulfuric acid at a particular scan time. Remember the potential region, plus 0.2 to minus 0.2. Very small, narrow region. Why am I interested in this region? Because I can understand what type of hydrogen adsorption happens on polycrystalline platinum. I have H alpha, H beta. Hydrogen is giving me a voltammogram where the oxidation peak and the reduction peak happen at the same potential. When the peak happen at the same potential, this is a typical signature of surface confinement, something attached on the surface, nothing diffusing at all. This symmetric voltammograms where the oxidation and reduction happened at the same potential. This is a telltale feature of adsorption. So here we have HS and HW are two forms of adsorbed hydrogen, both happening on polycrystalline platinum. If you ask institute techniques, inoperando technique, you can understand. And if you calculate the area of this peak and the area of this peak, you can calculate how much of hydrogen is adsorbed on this. And this is one way of measuring surface area of platinum. You have got platinum nanoparticles attached on this and record voltammogram. From this, how many microcoulombs are necessary to get a monolayer, we can calculate. So the area of these peaks will allow you to calculate electrochemically accessible surface area, which is different from BET surface area. So this method is used many electrochemists to calculate electrochemically accessible surface area by using materials. This is of course polycrystalline platinum, but platinum nanoparticles also you can do. So we are looking at the hydrogen side of polycrystalline platinum where hydrogen gets adsorbed because you are going to the minus side, minus 0.2, minus 0.1, 0. Accurately, you need to use a very good reference electrode for these type of measurements so that quantitatively the quantity of hydrogen adsorbed in first site and second site can be. You can also electrochemically desorb it. Just like thermal desorption, slowly vary, this hydrogen can be also pulled out and find out what is the energy necessary for pulling it out. Now you take the, see here we have seen only a small region, minus 0.2 to plus 0.2. The same system, if you look at in the entire potential region, this is what you get. So hydrogen adsorption, you can see now. This can be confirmed in a very beautiful manner. When you go to minus point, let's say minus 0.1 or minus 0.2, hold it for 2-3 minutes. So what happens? Hydrogen is continuously evolving. Different mechanism, Tafel, Herovsky, etc. But hydrogen is continuously evolving means it gets saturated. So you will see this peak area will increase. Holding the potential at various points, you can control the amount of hydrogen adsorbed. So HA1, HA2, HA3, etc. different sites. And you can also calculate the coverage. If you have a density function theory, you can even calculate how much is the energy involved in that. That's why theory and experiment can give you beautiful confirmation if you do these type of measurements. So HC1, HC2, imagine you have got both oxidation and reduction happening at the same potential. All these are adsorption, desorption peaks. And if you have a single crystal, PT111, PT100 phase setting, you will see all these dramatically changing the picture. This is on a polycrystalline, but single crystal will give you different type of data. Now you go to the other side, oxygen. Same thing is valid here. O1, O2, O3. These are all oxygen adsorbed on various sites. And you can see oxygen reduction also happening at a very large. So the area of these can be estimated. It is also a strong function of the phase it happens. So if you have a oriented, polycrystalline itself, but if you have phase setting, you should be able to correlate with respect to this. So this is a typical case where cyclic voltammetry has helped people. And you change with the scan rate. Some other scan rate, all this information will disappear. Here you have got at 0.1 volt per second. So changing the rate of sweeping the potential, you will be able to match with the adsorption, desorption time scale happening in the system. Yeah, I will not go to details. Under 10 minutes, I'll try to wind up. There are many other systems where voltammetry can be extremely useful. For example, you can see here. Yeah, this is one case where stainless steel corrosion, linear sweep voltammetry of stainless steel, passivation, see stainless steel. You can see now this current increase and decrease. Decrease means passivation by thick film formation. So all that can be understood by voltammetry. And here you will see some loop formation because there is something called nucleation over potential. So all that also can be understood by voltammetry. I will not go to the details. Some cases, passivation phenomena can be interesting, could be investigated by voltammetry. For example, you can see now here ABC. This is again from our own experiments carried out almost 10 to 15 years ago. You have a gold electrode, you have a potassium ferricyanide, ferrocyanide, you get a beautiful reversible peak. You can calculate all the quantitative parameters. When there is a self-assembled monolayer means you can have an octane thiol on the surface of gold. Complete monolayer, you will see all the redox processes are suppressed completely. Partial monolayer, you will get little bit of activity. So the efficiency of passivation of a surface, whether gold, silver, platinum, it doesn't matter. By a simple monolayer can be investigated by using cyclic voltammetry. Remember, in these cases, you have some pinholes formed. Pinholes will allow potassium ferricyanide, ferrocyanide ions to diffuse. That's why you are getting little bit of activity. So the evolution of the monolayer formation, initially multi-layer, monolayer, all that can be investigated by using external redox probes. External redox probes such as potassium ferricyanide or ruthenium hexamino, that could be done. The quality of the monolayer can be investigated by using voltammetry. And sometimes when you publish these data, you also need to follow a convention. You have a US convention and a IUPAC convention. Normally, when you follow books like Baden-Faulkner, you follow this. That means cathodic currents are positive. Reduction always is shown up. But European journals sometimes prefer other way. But once you understand, it may not be a difficult thing to do. I also told you about surface confinement. I did not elaborate, but surface confinement also can be quantitatively studied, where this again is thanks to Alan J. Bard and Anson, two people. They derived an expression where IP, P current is linearly proportional to scan time. So remember earlier voltammogram, we told P current is proportional to square root of scan time. When species are trapped on the surface, no freely diffusing, you will see a different signature. P current is linearly varying with respect to scan time. So in thin layer electrochemical cells, sometimes you do spectroelectrochemistry. That means you have an electrode. The electrode cathode anode difference is so small. It is much smaller than the diffusion layer. Such cells are called thin layer electrochemical cells. Sometimes you use optically transparent thin layer electrochemical cells for spectroelectrochemistry. In such very thin layers, where the diffusion length is smaller than this, you will see this type of behavior. Sometimes it is called surface confinement. The oxidation reduction peaks happen at the same potential. The delta EP is 0. Remember, other delta EP is 59 millivolt. So here you get 0, and that shows that surface confined species and their P current is linearly related to scan time. If you know P current and plot with its scan rate, you can calculate this gamma star. Gamma star is nothing but surface coverage. Monolayer, multi-layer, sometimes partial coverage, 0.1 monolayer. So the surface coverage can be quantitatively estimated if you get such voltammograms. So whenever you get such beautiful voltammograms where cathodic, anodic peaks happen at the same potential, don't throw away. This is something very beautiful because you are able to measure the coverage, even if it is very small coverage. So this is again another interesting aspect of voltammetry. One or two more examples. We have been investigating carbon nanotubes. What is interesting is multi-wall carbon nanotube or single-wall carbon nanotube, you apply electric field, they can open out. We call it as unzipping, longitudinal unzipping of carbon nanotube. Longitudinal unzipping means carbon nanotube, if you unzip longitudinally, you will get a graphene nanoribbon. Carbon nanotube, you unzip laterally, you will get a graphene quantum dot. Just breaking, chopping. Quantum dot whose dimension will be equal to width of the multi-wall carbon nanotube. So we have been working in this area with various systems. I will show you how voltammetry can be interesting. First voltammogram you get like this. If you cycle with the electric potential, slowly opens out, area become more and more. So as the area becomes more and more, you will see the known Faraday component become more and more. Remember, still there is not much redox activity because the concentration of some quinone groups on the surface, some oxygen groups are there, but they are very small. That is why initially 1 hour you will see this, 4 hours, 10 hours. As time goes and more, you will see the non-Faraday current increases with respect to hours, how much hours you treat. And you can also see these are different extent with a different type of materials. This is single wall carbon nanotube. This is oxide of single wall carbon nanotube. You can see so broad because conductivity is not very high compared to here. And here graphene, after forming graphene, how many orders of magnitude change happened on the non-Faraday current. And you can also see the peaks, oxidation as well as reduction, they become more. So you have several quinone groups generated on the carbon nanotube. All this could be investigated by using voltammetry. When we look at unzipping of multi-wall carbon nanotube, recently we did it in ionic liquid, or I would say more correctly, we did ionic liquid as well as superacid. Superacid because carbon nanotube, breaking, CC cleavage we are doing. CC cleavage, always you have a heterolytic or homolytic. Homolytic means free radical. Heterolytic means carbanion or carbocation. Carbocation can be stabilized in superacid. That's why when we did it in superacid, voltammogram you can see. Pristine carbon nanotube, you have a black curve, small amount of oxygen. That is why you get little bit of oxidation as well as reduction. Some quinone groups on the surface, or maybe even carboxylate. 6 hours you can see progressively it opens out. Towards the end you will see saturation. So the area change with the time, if you plot, it gets saturated by this area. That means complete unzipping happens by this many hours. TM is also revealing multi-wall carbon nanotube diameter. You can see this is a diameter. Open it out. If R is the radius of this, 2 pi R will be the diameter. Roughly a geometric correlation is seen in TM. That's why this data is beautiful because everything is open. And we did it in trifluoromethane sulfonic acid as the electrolyte, so that carbocation can be stabilized. Anyway, these results are going on. I just want to show you voltammetry can be revealing for this. For organic chemists, there is so much to learn by using cyclic voltammetry. If E represents an electron transfer reaction, either preceded or followed by a chemical reaction, cyclic voltammetry can be an extremely important tool to give you mechanistic insights, whether sometimes catalytic reactions, sometimes follow-up reactions. One example I will show you. A becomes B plus electron is an electrochemical reaction, heterogeneous electrode-electrolyte interface. But the moment B is forming, B disproportionates by a chemical reaction to form C. So this is a typical example of EC. E electron transfer, C chemical reaction. Electron transfer followed by a chemical reaction. Voltammogram with the variation of rate constant with the scan rate you can see. Scan rate, at some scan rate you get a beautiful reversible peak. Some scan rate you will see, no, it is only looks like irreversible. This side is so much suppressed. There is a small activity, it's not completely irreversible, but this variation is because of the variation of the scan rate as well as the rate constant. Essentially, Kf is the rate constant of the chemical reaction. K heterogeneous is the electron transfer rate constant. So a competition between these two, this could be irreversible, this could be reversible. Accordingly, you will get different shape of voltammogram. So you see here, Kf per second is the rate constant of the chemical reaction. So at 10, 5, as you change the rate constant, voltammogram undergoes a change in the shape. From that, you can predict whether the reaction is coupled with chemically or not. Typical example, ERCI. ER means reversible electron transfer, irreversible chemical reaction. This is what you expect with the variation of scan rate. CRER, chemical reaction is reversible, electrochemical also is reversible. You see, not much change. ER, 2 electron transfers followed. Some case you get 1 peak, some case you get 2 peak. So the difference between these peak, the irreversible ER1 and ER2 also can be analyzed by changing scan rate. So please remember the scan rate variation of these will allow you to understand the mechanism. maybe one or two examples. Take phenylenediamine as an example. You can see now you have got phenylenediamine, and then you have benzoquinone and hydroquinone. All that can be understood. Mechanism could be understood by cyclic voltammetry, what we call it as ECE mechanism: electron transfer, chemical reaction, and electron transfer. And there are much more variations in this. Many reactions are there where you get ladder type. Again, I will not go to details. Let me come back to some of the errors in voltammetries, maybe another 5 to 10 minutes. In cyclic voltammetry, whenever you apply a potential, especially changing potential, d by dt also gives you a noise called non-Faraday current. Every voltammograms you will have non-Faraday current. It is impossible for you to accurately correct it. Roughly you can correct it because it varies with respect to scan rate. This is sometimes called charging current, sometimes non-Faraday current. This is a function of area, capacitance, and scan rate. Capacitance in turn is a function of potential. That is why there is a complication for correction. Otherwise, if you assume capacitance is independent of potential, then you know the nu you can calculate. So the ratio of noise to signal. Signal is Faraday current, IP, P current. IC is the noise. Noise to signal depends on these parameters. Nu power half, and noise to signal or charging current to the Faraday current or P current, you can calculate as a function of nu power half. So high voltage and low concentration, several distortion happens in voltammograms. High voltage and very low concentration. That is why biosensors, if you want to measure with parts per million, parts per billion, you will have difficulties of this, and hence people go to differential pulse voltammetry. Similarly, double layer correction, sometimes you can see voltammogram. Here you see the signal is so small and the noise is so huge. So noise to signal ratio gets affected by these. This is essentially for porous electrodes. So very large porous electrodes, double layer capacitance, because ions get trapped in the pores, they contribute. You can see how you go from this to this to this to this. So the non-Faradaic or charging current, how it influences the peak shape you can see. Now this is very broad, this is very sharp, but this could be effect of double layer charging at different sweep rate can be calculated quantitatively, and you can do correction. Similarly, sometimes switching potential is important. EPC is your peak, but you can switch here, switch here, switch here, switch here. So you should at least go 60 millivolt from the peak. Why 60? Because RT by NF. Thermal energy is 59 millivolt. 2 times you do, much better. So if you get a peak, at least 100, 200 millivolt if you go and then switch. Otherwise, you will have a effect of switching. Reversal. Reverse part will be influenced by this. So it is important that once you get a peak, at least go 100 millivolt away from the peak and then you do the switching. Otherwise, voltammogram gets distorted. So these are all problems of switching potential. Again, I will not go to the details. Correction can be done because this decay is quaternion. So if you calculate T power minus half dependence, you should be able to calculate accurately. Similarly, multi-component systems, when you have 2 redox species and the peaks are more or less closer, then you will see 1 peak. Sometimes you get 2 peaks. So again, the rule of thumb is from peak, you go 100 millivolt at least, and then see whether it happens. Otherwise, both processes will happen at the same value. I don't know, some of the inorganic chemists may be remembering K.M. Cardy's work, porphyrin. Porphyrin, you have a ligand as well as your a metal center. So the redox peaks are, you can tune it. You can have both redox peak here or make it here, make it here, make it here. Redox tuning is possible by changing the ligand. Very famous work in porphyrin chemistry by K.M. Cardish. So this is exactly where you see multivalent behavior. So we have been talking about cyclic voltammetry for quite some time. There are several advantages I mentioned to you. Without knowing the detailed electrochemistry, people can use it. Organic chemists, inorganic chemists, all can use voltammetry using these benefits. Diverse systems can be investigated: metallic, semiconducting, even insulating. Insulating means you have to mix with some carbon or graphite, make it as a paste electrode and look at it. You will get redox activity. Layered double hydroxides, polymers, all that can be investigated because you need some conductivity. That is why people use graphite or super P or various forms of conducting carbon as an additive. Metallic, semiconducting, and even insulating. Capability of changing time scale is very important because you have competition between diffusion and electron transfer. By changing the scan rate means sweep rate. So from millisecond or microsecond to several hours, that is where it is possible. Capability of change in time scale I mentioned. Qualitative as well as quantitative information can be obtained. And if you do quantitative analysis, rate constant can be calculated from irreversible and quasi-reversible systems. All the thermodynamic information can be obtained from reversible systems, which means equilibrium constant, maybe the entropy, enthalpy, all that can be, even solvent contribution can be calculated. Mechanistic insights can be obtained, EC, ECE, homo-LUMO gap can be estimated, assuming that solvation is not changing the electronic structure. Conducting polymers is a routine thing that people use peaks and calculate what is the homo-LUMO gap. Soluble, insoluble, gaseous species you can do. NO can be bubbled in the electrochemical system, and you will be able to calculate using voltammetry. Capability of in situ and in vivo measurements, especially in biology, in vivo measurement is very important. And these days, it's also possible to have in operando techniques, like in batteries, while charging, discharging, you can acquire information by doing voltammetry. Limitations are there. Number one, we talked about potential scan. However rigorous mathematics you do, still it is very approximate because you are sweeping at a large rate. So from potential from one point to other point, in principle, you will be able to get preliminary information because potential, time, and current, that three-dimensional surface you are only cutting across. That is why preliminary information. Of course, you are changing time scale, you should match. That is why it is important if you are an unknown system you are investigating, go from low scan rate to very high scan rate and find out where you get good redox behavior. Qualitative as well as semi-quantitative. Then I mentioned that the calculations of rate constant, diffusion coefficient, etc. are imprecise. It is important to have an third party or maybe an independent technique to validate these numbers. Dependence on working electrode is a big problem. You record voltammograms, especially complexes, transition metal complexes, ruthenium, etc. You use of classic carbon, you will get one behavior. Use platinum, you get different behavior. Now, what type of interaction happens on the platinum, similarly, you change the supporting electrode, you get different behavior. Those are the things which we need to be careful. Dependence on working electrode. Influence of counter ions. Sometimes you will have adsorption. Common mistakes in cyclic voltammograms include many people, even published papers, you will see people talk current rather than current density. It is not correct because you will not be able to verify independently. Even if you don't know the area, approximate area, apparent area can be used. That is a common mistake. No scan directions. People don't show what is the direction because from open circuit, you go cathodic or you go anodic, different voltammograms will come because that is where, especially the first cycle, whether you are producing oxidized species or reduced species, based on that, the entire voltammetry pattern will change. That is why the scan direction is very critical. Many people don't mention working electrode, platinum, gold, silver, classic carbon. That is also not mentioned. No indication of OCP. Actually, open circuit potential must be mentioned. Then only it makes sense. Where your starting point, initial value, whether some Faraday reaction happens or not, we don't know. No cycle number. Many cases, voltammogram dramatically change. First cycle, second cycle, third cycle. So what is important is we report only third or fourth cycle, making sure it is a representative voltammogram. First cycle, initial cycle effects are very difficult. It depends on the substrate quality. Suppose you make a conducting polymer on glassy carbon or ITO or FTO or different type of substrate. What type of nucleation overpotentials are involved, we don't know. That's why record through 3 times and see whether reproducible and record it. Solvent, electrolyte, working electrode, not specified. Many people do extrapolation to tafel by low scan rate. It's actually a wrong practice at all because you cannot translate this into a steady state technique. That's why low scan rate, voltammogram and using tafel equation is again completely wrong. CV for half cell is very crude. You must always need 3 electrode system to understand cyclic voltammetry because you are supposed to change only the working electrode by applying a linear variation. While other case, your counter and reference are together. So that is also changing. So how much of the externally applied field is going to working electrode, you don't know. Normally assume 50% here and 50% there, but that will be incorrect. Now, I will not go to details. Look at this. This is important because methanol oxidation. You see a forward peak coming back and a reverse peak happening. Reverse peak is actually poisoning of the catalyst. Platinum, palladium, ruthenium. You will see methanol oxidation. You will see forward, go back, come back, and then there is a reverse. So the forward by reverse or reverse by forward, this will allow you to quantitatively express the extent of poisoning. That's why this technique is important. Voltammetry can allow you the positioning of the electrocatalyst when you are looking at methanol oxidation or such things. Oxidation happens because CO is adsorbed on platinum. Platinum gets poisoned. And as a function of cycle life, here is a literature taken with various compositions. Similarly, many batteries, this is a sodium-ion battery example, no scan direction is given, and you will see first cycle, second cycle, third cycle, there is so much of inconsistency because after first cycle, you will see many of the peaks are disappeared. Okay, so these are cases where scan direction would have been very important. Scan direction to show whether first cycle is going anodic, cathodic. So these are examples, and the extreme case is where TAFE. You cannot use cyclic voltammetry low scan rate to get TAFE. TAFE is a steady state technique. TAFE means you plot low current versus over potential, and there are at least 3 criteria. You should have at least 1 order of magnitude, log scale. You should have linearity. You should be away from the limiting current because TAFE assumes that you have electron transfer, no mass transfer. So you should be away from the limiting currents. Limiting current is what you get it in cyclic voltammetric peak. That's why it is incorrect to extrapolate from cyclic voltammetry TAFE curves. Anyway, again, I will not go to details. Yeah, maybe last 5 minutes I will talk about ultra-microelectrodes because this is where many, I mentioned to you about many eye-opening developments in the size of electrodes. Very small electrodes you make. So very small means smaller than the diffuse layer thickness. Typically 5 micron, 1 micron, 2 micron. People have been using such electrodes in the past. 1970, Fleischmann used a small electrode. They found unusual effects. They mentioned it as non-quaternion diffusion, non-Fickian diffusion. It's not like as per Fick's law, but later we understand that size is playing an important role. In 1981, Wyman made very small electrodes. 1996, nano electrodes, very small sizes, and now it is routine in electrophysiology and neurology to use such electrodes. What is interesting about this electrode is the time dependence which we saw will vanish. Why does it vanish? Because the diffusion conditions are entirely different. So two aspects, time invariant current. Current becomes independent of time. Steady state is obtained very fast because electrode size is smaller than the diffuse layer thickness. Scan rate no longer affects size and shape of voltammogram. These two aspects have been given a variety of new investigations by using voltammetry. This is just to recollect. Thin layer electrochemistry is where you get these symmetric peak. Conventional electrochemistry you get last when the size of the electrode is very small, you get a sigmoid voltammogram. Sigmoid voltammogram you can get. Why is it we are getting sigmoid? Because in such cases, the diffusion has two terms. First one is what we call it as time independent. Second one is time dependent. Remember the second part is quaternion, but that is valid only different time scale. First one is more important. First one is called radial diffusion. So if the size is extremely small, radial diffusion is more dominant than the conventional, what you call the normal diffusion. So this expression, first expression becomes more important. There is no time in first expression. As the electrode shrinks, electrode becomes smaller and smaller and smaller. You get the first expression become more and more important, and hence longer time scales, faster scan rates, shorter electrode time scales. You will get this is 100 times larger than the second term. So you will see that I of t is independent of t, and it all depends on only R. And the expression is very simple. Current is 4NFADCO. There is no other term coming into picture. So the current depends only on the radius and the concentration. If you vary the radius, you can measure the concentration. So these electrodes are called ultra-microelectrodes. You can go to very high scan rates, 1 volt per second, 10 volt per second. You can imagine. So the same size of electrode, change the scan rate, how the voltammetric shape changes, you can see. And remember the current nanoampere, 2 nanoampere per square centimeter. Femtoampere can also be measured by using this technique. So you use an ultra micro electrode. You can go to 50,000 volt per second. Many redox proteins can be investigated by using fast scan voltammetry. This is a development which happened during last 20-30 years. So, and remember currents are nano and femto. So IR drop will not affect your voltammogram. No IR compensation, nothing is needed because the I into R, I is femto. You multiply even kilo ohm or mega ohm, still current is very small. That is why signal to noise ratio is not very important with such ultra micro electrodes. I will not go to details. Again, the quantitative aspect, I can skip it. Remember that fast scan CV. of anthracene, you will see same thing we saw earlier. You can do electrochemistry without supporting electrolyte. In inorganic chemists are sometimes in dilemma. You add so many supporting electrolytes, will it affect my chemistry or not? This can be investigated by using supporting electrolyte less voltammetry with ultra-microelectrodes. For example, I'll show, these are the two last slides. One example where we did some exotic thing. We took a peanut leaf. Peanut leaf has got guard cells and stomata. So when stomata opens, oxygen comes out. So we are interested to investigate stomatal opening. By opening can be artificially, stomata can be also opened. You put some vanadilyl ion, stomata opens. When stomata opens, gas exchange happens. So oxygen reduction can be investigated at the stomatal opening. So this is a system where a platinum ultra microelectrode, PTUME, you can see, is immersed, and then you have a platinum electrode where a stomatal leaf is attached after removing chlorophyll, spongy parenchyma, and this is a guard cell. So oxygen coming out can be detected by using an ultra microelectrode. And the voltammogram is very, very broad, but potentially will confirm that it is oxygen. So this is an example where you used an ultra microelectrode to investigate an insulating system such as a plant leaf. Of course, this is a peanut leaf after removing the chlorophyll. So you can investigate these type of crazy things by using ultra microelectrode. Similarly, we used an all solid state measurement. We have a Teflon cell where we have an ultra microelectrode, and in naphthalene we dissolve some potassium ferricyanide and then investigate it. Okay, in solid phase. Again, I will not go to the details. So let me just summarize. I've been talking about cyclic voltammetry and its cousin linear sheaf voltammetry. We have got several uncertainties. You can imagine in real cyclic voltammetry, Faraday's response is superimposed on a roughly constant charging current. But it is roughly constant because potentials and capacitance, they depend, they change. So the forward and reverse, there is no guarantee that the same dE by dt is there. That is why there is an error due to dE by dt. It's an assumption that a sign only changes, but no, it can vary forward and backward. You see, the non-Faraday current can dramatically vary based on the potential. So both peak currents in CV are imprecise because of the correction for charging current, typically uncertain. Second important is for the reversal peak, impression is increased further because one cannot readily define the folded Faraday response for the forward process as a reference for the measurement. CV is not the ideal method for quantitative evaluation of properties from peak height, such as concentration of a species, especially for biosensors people use. Rate constant of coupled homogeneous reactions, etc. are inaccurate. Method's power lies in its diagnostic strength, derived from the case of interpreting qualitative and semi-quantitative behavior. Once you understand mechanism, you can use these techniques. So steady state measurements are of your best and reliable friend to investigate electrochemical studies. Steady state means galvanostatic or potentiostatic because d by dt is 0 there. You apply a small current, wait for a steady state, look at that value. Again, apply more current, go to the steady state and plot all the steady state values because d by dt is 0. So I hope I have given you a feeling why cyclic voltammetry is important as a tool, very powerful electrochemical tool because organic chemists, inorganic chemists, material scientists, neurochemists, all of them use this technique. Preliminary information can be obtained without understanding the electrochemistry at details. If you want to understand the electrochemistry details, you may have to read books like Baden-Faulkner. This little bit of mathematics is essential because everything is based on fixed laws, and then first law and second law, and then you have to solve those different equations with the boundary conditions. We use linear, semi-infinite diffusion, and sometimes even Laplace transform to solve these expressions. However, without knowing all that, you can calculate rate constant, diffusion coefficient. That is the strength of voltammetry. Macroelectrodes and microelectrodes, so much of difference. Thermodynamic and kinetic information can be obtained. Cycle dependence, I did not talk much. 1, 2, 3, you can do cycle dependence. 200, 300, 500 cycles can be done to look at durability of electrocatalyst. Morphology, conductivity changes, growth, standard dependence, all that can be investigated. Ultra microelectrodes allow you in unconventional media, ionic liquids, microemulsions, not very conducting in terms of ionic conductivity, but you can still do it. Microemulsions, the CMC, surfactants, the critical micellar concentration can be also detected by using voltammetry with external redox probes. You can also, interestingly, all solid state measurements are also possible. Mechanistic details, in situ, in operando, and in vivo. These are all going to be more important in the future. Solid state devices, device as such can be investigated. Chemical field effect transistors, insulating gate field effect transistors, ion sensing field effect transistors, NFET, MFET, they are also amenable for you to do voltammetric studies. Lastly, biosensors, lab on a chip, all these cases. Now it is interesting that you can use artificial intelligence with not one working electrode, hundreds of working electrodes. It is possible that by photolithography, you can have several working electrodes and a drop in microfluidics, as the drop goes on the side of the wall of the microfluidic chip, you can have a working electrode, individually addressable. So that is why where AI is going to be a big deal. You will get so much of data, and you don't one drop of blood only in this device. Drop flows. During that, you collect all information. I can do analysis in real time. That is why it is going to have further revolutions in the future. Already Google Glass and all that, people are able to use this for voltammetry. Of course, misperception to get kinetic parameters. And I have a couple of references given here. The last reference, number 5, by James Rusling and S.L. Cube is very good because insulating materials, polymers. There's an old paper in Advanced Materials, 1994, a wonderful reference for people without knowing electrochemistry. You can use this technique. Other one, of course, you need introduction to cyclic voltammetry, journal of chemical education. Recently, there was also in ACS Nano, there was some article about voltammetry as a primer. And Heinz Anglicum reference is more about ultra-microelectrodes. And this one, Journal of Chemical Education, 1983, is also an old paper. So you will be able to look at this. Journal of Chemical Education 2018 also is a very interesting paper. So if you want to read all this, if you have any doubt, I'm sure I'll be able to explain to you. Of course, I did not talk about my research. We have a small group. The 2 students are there. Sneha is working on flexible electrolytes for future power sources, and then Vikas works on phosphorine quantum dots. Electrochemically, you can make phosphorine quantum dot from black phosphorus. You deposit black phosphorus from glassy carbon, apply electric field, you'll be able to, because black phosphorus has a layer structure, just like intercalation. You can allow ions exfoliate and form small phosphorine quantum dots that show size-dependent luminescence. So others, some of them are BSMS students. With this, let me thank. I think I spoke more than 1 hour, but I'm sure we can discuss. If you have any doubt about any of this, I'll be happy to answer. No, these were 2 different. Reversible, the basic rate constant. Rate constant should have also some time scale. Some time is different. For example, most of these classifications are reversible, irreversible, and quasi-reversible depends upon one composite parameter called lambda. Lambda has standard. Standard means time is built in that. Multiplied by rate constant. Numbers I show. About that. Yeah, so you take 100 milliwatt per second as a typical standard. Okay, then irreversible, you will see both. Irreversible, you will have only one peak. Quasi-reversible, you will have peaks, but they are far away. The EPC minus EP will not be as you expect. That is number 1. Number 2, peak current will be much smaller than the reversible. Second parameter is the width. As becomes more and more irreversible, peak width will become more and more large. As the standard. So there is also an expression will tell you one order of magnitude change in scan rate. That means 10 become 100, 100 become 1000. How much the peak width variation? That can also be estimated by you. Most of these cases, the logarithmic scale is important. So scan rate from 1 to 10 to 100 is important because then we can predict how much the peak shift. Yeah, yes. Does it clarify? Quasi-reversible is a term. Many people don't believe. Inorganic chemists traditionally use quasi-reversible. Sometimes scale between fast reversible and irreversible. Okay, but rate constant can be estimated from quasi-reversible from the peak. Okay. Yeah, please.
Inverse flow diagram.
Yes. Or silver. There should be a common ion. If there is no common ion, you get a liquid junction potential. Liquid junction potential can be estimated. There are expressions. If you know the mobility of the ion and transport number, you can calculate liquid junction potential by an equation and there's an equation. It's always better that you have a common ion. So liquid junction potential will not be.
Some research articles.
In the research articles, they put AgCl in all media.
Yes, sir.
Not correct. If you are doing chloride media, AgCl and calomel can be. If you are using sulfuric acid, you put chloride. What happens? Cl minus will go and that's all. So the Cl concentration keeps on changing because from AgCl, you have some chloride. Chloride actually electron whether it's a solution. Slowly chloride will diffuse into the system and it will contaminate and it will change. And also this is a time dependent phenomenon. The reason why we say don't use AgCl in sulfuric. Sodium sulfate, then you should use mercury mercurosulfate.
Sodium sulfide and
sodium sulfide, you can use sodium containing. There may be some sulfate containing reference electrodes also. You have to check a book called Ibis and Janus, Theory and Practice of Reference Electrodes. You may find something actually accurate for sulfate or depend on the common carbon. Na plus. So sodium calomel you use. If you are using Na2S, instead of normal calomel you use saturated calomel, mercury mercurous chloride in solution ACl. Instead of that, you can use sodium chloride solution. So Na is common. Understand that there should be a common ion, so there will not be a junction created. If possible, you have a common ion, the liquid junction potential is very small. Very small means 5 millivolts. Yeah, chapter 3 from Gordon Faulkner. Okay. V. What is liquid junction potential? How to calculate? What are the common ions? Liquid junction potential three types. One is only a constant cell. 1 molar KCl and 1 millimolar KCl. This will give you a little bit. You can calculate the concentration cell and liquid junction potential. But ions are entirely different. Mobility and transport numbers are different. You will have large. Yeah, go ahead.
So many diagrams.
That is, I understand. That is our own work. Yeah. That is our own work. I can.
How many signals you can expect?
Yeah. No, it is not number of gold. That depends on the size of the gold. If you get 3 nanometer, we got 6 plus. It's more than 8 nanometer, it came down. Then it won't, you don't see at all. So the bulk gold, you know, are auric and auros only, right? When it becomes 3 or 4 nanometer, this is what we talk, right? We have shown already several charge states. You can, so you can see somewhere, you can measure the 0 and then you go 1 plus, 2 plus, 3 plus, 4 plus, 5 plus, 6 plus. By the time you come here, molar undergoes degradation. Similarly, you can do 1 minus, 2 minus. This is called what is called charge number. There is some concept called point of zero charge. Okay, potential at which surface charge is used. So based on that, we will get multi-valent redox behavior. 2.2 nanometer and 2.6 nanometer. This is the important plot. This is called charge number. See, 6 plus, 6 minus, 5 to 6 redox states could be accessible for these ultra small particles. This is what you are talking about, right? Yeah. This is my stabilizer will not allow. The size is more critical. Stabilizer will be, for example, you can have a octane thiol or maybe an amine. Amine can be attached to make it stable. Okay, but the protective layer does not affect your. This property is intrinsic. So what is critical in this case is the size. For example, if the size is 4, 5, 6 nanometer, this size property disappears. This has been investigated by many other groups. I mentioned about Royce W. Murray. Royce W. Murray did it for gold particles. But rhodium, platinum, carbon, many systems in such small size shows this multivalent redox behavior. Yeah, so here, actually, you can also measure diffusion coefficient as a function of charge number. 1 plus 2 plus 3 plus 3 plus will move much faster. Whether it is diffusion or migration is difficult, but you will see evidence about the movement, and the hydrodynamic size also vary. This is in solution. It is possible to calculate the hydrodynamic size by measurement of some of the solution properties. So in fact, again, Royce W. Murray did pioneering work in this using gold. What we have shown here is graphene quantum dot. Again, almost 10 years ago, one of my students called Dhanraj Shinde, he was in NCL working. So he has found this and we published in Anglicom 2013. You can get more details in that, but the charge states which you got are somewhere around 6 both sides. Yeah. But more than 7-8 nanometer, this wall phenomenon disappears. Yeah, please. Materials you should be able to research. When the morphology is changing dramatically by doing either, thing, you should be able to see the field. In carbon nanotube, whether some periodical formation, etc., the number is so small that very difficult to look at. Mass spectra, in situ mass spectra, if you do differential mass spectroscopy, probably will get evidence like this last period. Other carbon, general, any carbon-carbon bond breaking, we should be able to find it. Anything other? Yes, phosphorus also we should. I mean, phosphorus might happen P breaking, I don't know. Phosphido and other can come in between. Yeah, 2D materials, sanding, phosphorine, etc. Yes, please. Yes. Yeah, I can tell you that. To go to. Yeah, this is right. Yes. What happened is cyclic voltammetry, even if you are applying very low scan rate, dE by dt is appreciable. dE by dt is appreciable, and the C capacitance, which is contributing to the non-Faraday current, C is a function of potential. In steady state techniques, dE by dt is 0. So steady state technique, steady state means potential is not changing with respect to time. That means capacitance is also not changing with respect to time. So when dE by dt is 0, non-Faraday current is 0. Now, to get steady state current potential curve, you can do two approaches. One is galvanostatic, constant current. You pass a small under equilibrium, no current, then pass small amount of current, wait for equilibrium, plot the potential versus time. If it is not changing, now increase the current, microampere, milliampere, finally till you get the limiting current. Now you can also come back to equilibrium and do it on the other side. This plot we call it as galvanostatic current potential measurement. But it's a steady state measurement. You understood? Every time you wait till potential is constant. Okay. This galvanostatic steady state measurement, you can also do potential statically. Some systems where the surface gets passivated, stainless steel, cobalt, nickel, you do potential statically. Open circuit potential, zero current, and potential can be 100 millivolt you increase. Wait till current is constant, measure the current. So steady state measurement can be carried out potential statically or galvanostatically. Now you plot this log current versus potential or your potential. You are changing the potential. The difference between the equilibrium potential or open circuit potential and the potential is called eta or potential. So you plot eta versus log current. That is what is the TAFL. Okay. Now, three criteria you have to apply. Since we are talking about Taffel equation is irreversible, unlike quasi-reversible or irreversible, you understood? That means in the Butler equation only forward, either oxidation or reduction only you are interested. To make sure that you are only in irreversible, go 100 millivolt away from the open circuit minimum. That means three criteria. First criteria is overpotential should be above 100 millivolt, 100, 200, 300, no problem. That means you are away from equilibrium. That means you are away from the reverse process interfering with you. So first criteria is overpotential should be larger than 100 millivolt. Second criteria is at least one order of magnitude linearity is needed because you are plotting log 1 to 10, 10 to 100, 100 to 1000. This is a semi-log plot, right? Eta versus log I. So second criteria is at least one order of magnitude linearity. Third criteria is you should be away from mass transfer limit. If you know the limiting current, 1/10 of the limiting current there, you should stop. Limiting current means you get like this in limiting current. Okay, so 1/10, suppose this limiting current you know, 1/10 of that you should stop, so that you are in the logarithmic region. So these three criteria can be used to get a good reliable Taffel's law. Now theoretically you can get Taffel's law of RT by NF, 2.303 RT by NF, 60 millivolt, 30 millivolt, 120 millivolt, 90 millivolt, that's all. Does that answer your question? Yeah.
Chronoamperometry is used for identifying operating potential window. For how long we need the electrode at a vortex potential.
Is used for chronoamperometry means current versus time. Hello? Oh, you have to speak there. You have to speak there. If chronoamperometry is used for identifying operating potential window, chronoamperometry cannot be used for estimating operating potential window. I do not agree. Chronoamperometry means current versus time. Potential window, we have to look at what is the minimum potential and maximum potential. Both these potential windows always should not decouple. Potential window is more related to the system we have. For example, sulfuric acid, we have a potential window. Acetylnitride, our tetrabutadiene flow point and the potential window. So the potential window depends on the thermodynamics of the electrode electrolyte system. Chronoamperometry can give you for a catalytic reaction, the current varies with respect to time. I versus E power half, diffusion coefficient. Now, various potentials, you can take current versus time. If you know these various potentials, at least this sense and that length, I versus T, if you look at it, I is not changing with respect to T, the potential figure can be used. How long we need to maintain the electrode at a vertex potential? We decide potential limit based on final stationary current of T. Yeah, I believe that one question is very important, the vertex potential. The vertex potential, if reaction happens, reaction should go to a zero surface concentration. That is what you take in the peak. So we must arrange in such a way that current decays completely, at least exponentially, 73 or 79%. Hope that answers. Yeah. Okay. Thank you, Ashwin. Thank you all. Send me an email. My email ID is there. Yeah. Okay. Thank you. Okay, so thank you for the meeting. Oh, okay.